Now we want to show the approximate Posa conjecture. Note that you have a graph with the minimum degree, at least 2/3 plus alpha plus n. You want to find the square of the Hamilton cycle. So we may assume that alpha is at most 1/100, and then beta is like alpha over 3, then epsilon is small. Or you can just simply write this. But with these choices, I mean, you can specify the relation in a more concrete way. Okay, so, and yeah, n is small enough so that all the previous lemmas hold. Now we use absorbing lemma. We find the, I mean, absorbing square path, PA, with this many vertices. Furthermore, that absorbs any set of alpha to 20 vertices. Okay, so now we project this path, square path here. So this is PA. The remaining part is has mean degree at least 2/3 plus beta times n. Okay, technically, instead of n, you can write the number of vertices here. By using reservoir lemma, find R such that let's say property R1 that its side is like this, and every vertex P and spans enough number of edges towards this R, meaning that this side is bigger than 2/3 plus beta over 2 times R. Okay. So what you know is that for any U, which is small, and four vertices A, B, C, D, you know that the graph G, you take R and then you project this U, and then in the remaining one, you take the induced graph with AB, and then you add this A, B, C, D. Is what? As again, mean degree, at least the this so that the connection lemma provides a square path from AB to CD. Okay, so we know this. So from this reservoir, together with the property of reservoir, together with the connection lemma, you can always do it. As long as, you delete its many vertices. Every time you use some vertices from reservoir, next time you apply this principle, you put the already used vertices into U so that our square path, all the vertices are distinct. Now what? You have this PA and you have this R. And then now you want to extend this PA into a longer square path. And ideally, you want to cover as much as possible, except very small left, and then that small will be absorbed into this PA. So, what? This is square path, and this PA is small. Now what? For these two, you take a common neighbor, and for these two, you take a common neighbor. For these two, you take a common neighbor. So this will extend it. So we extend this PA by repeatedly taking common neighbors of an end pair of the current square path. So what? You can extend, say that you have this like PA and P prime together is this P. This is a square path. The P of length at least n over 3. Why? Every time you do this, these two vertices, each one of them has a degree at least 2 over 3 plus beta times n. And that means they have at least 1 plus 3 plus 2 beta n common neighbors. And out of them, you forget the ones that's assigned to R. So that's not going to be used. The previously used vertices, that's not going to be used. So if this one is smaller than 1 over 3n, and this R is small, then you can keep do this. So you will get stuck once this has length at least n over 3. And let P prime be this extended part with this P prime is x1, x2 to xl. So here x1, x2, xl. Okay, and let P be the remaining part. So the remaining one is T. If this T is smaller than epsilon n, we are done. We want to keep extend this until this one is smaller than n, epsilon n. Okay, now what? Now what we want to do is consider the case that some vertex here, either it has many neighbors inside of T or many neighbors towards there. So essentially, its standing edges here are not so much. It's like, beta to the less than beta to the 10 of n. And its number of edges towards PA is also not large because PA itself is small. So n must beta to the n. So either it's sending most of the edges towards P P prime or inside of T. Okay. And let's first consider how we deal with it if many vertices here sends the edges to P prime. If you have this P prime, x1, x2, dot, 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 xl, if there is vertex which sends like edges to 4 consecutive vertices, then you can just take this path instead. It's sending this, so you can just insert this into here. So we are happy. Otherwise, so that's never happening. We can assume. Otherwise, you insert it to get a longer P, and then you repeat this. At some point, you are stuck. And what can we say is that this vertex has degree roughly 2n/3, a bit over 2n/3. So what we can expect is that on this P, it's also sending like 2/3 of it. So like sending 2 edges and 1 non-edge, 2 edges and 1 non-edge. That's the normal behavior. That's average. What happens in average. However, we know that its neighbor, it's sending actually strictly bigger than 2n/3. So sometimes it has to be 3 consecutive ones. So assume you have 3 consecutive 1, 2, and 2, 1, and again 3 consecutive 1. Then what happens is that it's spending like 3, 2, 2, 3, so 10 neighbors and 3 non-neighbor. Assume you have a similar one, so another vertex, say, let's say last one we don't care, so 3, 2, 2, 2, and another one again 3, 2, 2, 2. So let's say this is x, y, and then g, w. 4 of them are all sending this way. Then what you can do is that you take these two and then put y. And then you delete this. You delete this. So you take this y and then you take this. And then g, you took this and then you delete this. W, this, delete this, and then x, this. So x and deleting have the same. So this is x, this. Then what happened? So 3, 2, 2, 3, but now you insert something, insert something, and then there are 2, insert something, and then 2, which are neighbor, and insert something and 2, insert something and 2, insert something and 2. In fact, this y is adjacent with this 4, all these 4, and this g is adjacent with all these 4, and w is adjacent with all these 4, and x is adjacent with all these 4. So in short, you can kick out these 3 vertices and then insert these 4 vertices so that you get a longer path. You can elongate your square path. So this is something that we will use. So for this, what we do is for each vertex A outside, we define a string, the I sub A, which is I1 to IL, which is in 0, 1 sequence, such that IJ is 1 if and only if xj is a neighbor of A. So for this, say A, let's say this one was A, then IA was like 1, 1, 1, 0, 1, 1, 0, 1, 1, 0, 1, 1, 1. So 1 indicates its neighbor. So we are encoding this information. Why? We want to collect several vertices which has the same pattern like this, so that we can kick out this 3 and then insert this 4. So we may suppose that this IA do not contain any 4 consecutive one. As otherwise, we can extend this P prime by inserting A in the middle of these 4 neighbors. So we say like this. So this is maximal length of like maximal consecutive one. Let's say this is 3 block, and this is 2 block. This is 1 block, and this is 0 block. So this is block, this is 0 block, this is 3 block. Then this IA consists of, say, some J blocks, or J is 0, 1, 2, 3. And say substring of this IA is an interval, say. If it starts with 3 block and ends right before the next 3 block. So 1, 1, 1, 0, 1, 1, 0, 1, 1, 0, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0. So this is an interval. And an interval is heavy if all blocks are 2 block, except the first 3 block. Okay, now what? Now we will show that the above operation can be done if there are 2 things hold. If, say, if there exists some I such that you take the SI okay, so let's write it this way. So let's say SI has all the vertices in here, where this AI has a heavy interval starting at this XI. So for each I, you consider this sequence, and then that has several heavy interval. And then each heavy interval, let's say, oh, it starts at somewhere. And at this XI, if it starts, then you collect it in SI. And here, there is this I such that the minimum length of the heavy interval beginning at SI is less than, say, this. So for assume that there is a certain I such that you consider this SI, and it contains many vertices here. For each vertex, you consider a heavy interval starting at here. And for A, it has length, say, 10. For B, it has length 13. For C, it has like length, I don't know, 16. And you take the minimum length, which is 10. And that length is smaller than this. So assume this happens, then we will show that our previous operation is possible. And then later we will show that we can find such I so that we can do this operation. So for now, assume this. Then what? Let A be a vertex whose heavy interval beginning at xi is open. Minimum length, and say that's 3k plus 1. Then what? In P prime, we take this like is subpath, which like starts from this xi, and then let's say that's y1, y2, y3, c1, y4, y5, c2, y6, y7, c3, and like ck, y 2k plus 2, y 2k plus 3, y k plus 4. And then this is same as xi. Then what? A has all the neighbors. All y's are neighbors of A. Yj are all neighbors of A. All yj are neighbor of A. Then gj are not neighbor of A. And this is the minimum heavy interval, and then it's followed by 1, 1, 1. So neighbor, neighbor, neighbor. And what happened is that by the minimality, for every B in this SI, what happened? Its B also stands the 3 edges here, and then no, and then 2 edges, and then no, 2 edges, and so on. And then this B might have a longer interval. That means it's same interval, then it's exactly the same pattern. If it's a longer interval, then after this, you still send the 2 edges, and this might not be the edge. But except the last one, it has the same pattern. The substring of IB corresponding to, say, this part is like a Q prime, which is sub part of the subpath of this P prime. Q prime is the same, possibly except the last one. And as our S1 implies that this Si is at least K plus 1. So this has the length 3K plus 1 means that if Si has size at least K plus 1. And we choose the B1 to PK other than A. Then what we can do, we replace its Q prime by its Q double prime, which is what? Y1, Y2, and then B1, Y3, Y4, and B2. PK, then Y2K plus 1, Y2K plus 2, and then A. Because other ones, the last one might not be a neighbor, but for A, we know that the last Y sub 2K plus 4 is a neighbor. So we put A at the end. Then what? We know that each PI is, has a YI as a neighbor. So this sends all 4, this sends all 4, and this sends all 4 neighbors. And then Y itself, is square path, so they are all neighbor. So this is actually a square path. But what? We have kicked out K vertices, but we have put K plus 1 vertex. That's possible because, we have like this 2 additional one, 3, 2, 2, 2, 2, 3. And then instead of that, you rearrange it as 2, 2, 2, 2, 2, 2, then you get the longer length. So you will do that. Then we obtain a path longer than a square path P prime. And we call this the operation, say, swap. Okay, so now we have collected that if S1 holds, its property holds, then we can make the path longer, square path longer. We can extend it. Now we show that if many vertices in T, so T is the remaining vertices, there are at least like size epsilon n, such that all A satisfies, say, it sends lots of vertices in P prime, then we show that we can extend this P. So let's prove this. So for each vertex in this U, we know that we consider this string, let's say it contains P heavy interval. You count it, and such that the size of the union of the heavy interval is F. Then what? For each this, we count the number of neighbors here. What? So out of this heavy interval, you have 1, 2, 3, x, 1, 2, x, 1, 2, x, 1, 2. So what? In each heavy interval, you forget the first part, then later one, exactly 2 out of 3 vertices are neighbor. And again, you have the next heavy interval. Again, except the first one is 2 out of 3. So out of all together, it's f. But you delete 1 from every one. So f minus t fraction is actually 2/3 are neighbors. And then each interval, you didn't count this one from each heavy interval. So that much is your neighbor. And then if you have an interval, you start from 3, the block of length 3. And then at some point, you have a block of length smaller than 2. And overall, it's the ratio between neighbors and non-neighbors is, again, at most 2 out of 3. So 2 out of 3 on the last interval. This is upper bound on the neighborhood. I mean, the number of neighbors of A. And you can show that this is at most like 2 over 3 times L plus T. But we know that we assume that all these vertices then strictly bigger than 12 over 3 neighbors in T. I mean, P prime. That's what? If T is at least like this minus 2 over 3L, which is epsilon at least epsilon L. So for each vertex, you have many heavy interval. Hence, every A, so for every A in U, this string contains at least a epsilon n heavy interval. Okay, so, and we say that the heavy interval is short if it is of length less than, say, 20 epsilon to the negative 1. Then what? Then you want to show that for every A in this U, there are many short intervals. So at least like half epsilon L short heavy interval. Right? Otherwise, if not, then what? The size of the union of heavy interval is what? Out of epsilon L, effective epsilon, half epsilon L, left of them are not short. So these many are not short interval. And not short one has length at least 20 epsilon inverse, which is like 10 L. Like that's bigger than M. L is at least 1 over 3 N, which is a contradiction. The number of vertices is at most N. So, what do we know? You have this many short heavy interval. So, you have this x1 to xl, and for each a, you have like short heavy interval. And then the next one, you have short heavy interval. Next vertex, you have many short interval. And some of them start at the same one. So we can use the pigeonhole principle. So by pigeonhole principle, we can check that there exists I, index I, such that the short heavy interval begin at xi, or at least what? For each u, you have like this many short heavy interval, and that many whole heavy intervals start at this point. And then there are L such choices. So out of L choices, so on average, like this many distinct vertices in the U. Then what? We choose such I, and then let Xi be the set of those vertices. Then its Xi has like bigger than that, but n is much larger. So we know that this is like 3 times 20 epsilon to the negative 1 minus 2. So that's satisfying this S1. So what's S1? For this S, what? Minimum length of heavy interval is less than this. But what was that? Minimum length is smaller than that. Then this is like smaller than length is smaller than 3 times Si minus 2. So maybe I didn't write it correctly here. So 3 times this is what? Bigger than 3 times this minus 2, and that's bigger than 20 epsilon to the negative 1. Anyway, it satisfies S1. So we can perform swap operation at this I. And that proves the claim that we can extend this P. Okay, now with this claim, what do we know? Let U be the all vertices in T which spans more than two over 3 plus epsilon fraction of the vertices in P prime. Then what? This is more than epsilon n. And for the rest of them, what? The number of neighbors inside itself is what? its degree is at least 2 over 3 plus alpha times n. Then you subtract at most this much, because this is not in U. And you have to subtract R and then PA. We don't care whether it sends all of them, or all we know, all of them might be a neighbor of this. But you can easily check that this is strictly bigger than 2 over 3 times t plus linear term, alpha n over 3. Now what? You have this PA, and then it's P prime, and then you have R, and then here you might have some U, and then here everything is T. So that means in here we have high minimum degree. So this implies that any pair in here has at least alpha n over 3 common neighbor. That means you take this, and then you take the common neighbor, and then you take these two, take common neighbor. You take these two, take these two, take common neighbor. You take these two, common neighbor, and so on. You can again grow square path. Using this, we can find square path in t minus u of length bigger than alpha n over 3. And what? You take this end vertex here as A and B, and then here this end vertex as C and D. And then you use the connection lemma to connect it through this R. Use connection lemma to connect this with P using the almost 200 vertices in R. Then this will extend P. And you repeat this. And then with the use new P, you again check whether there is vertex which has 4 consecutive neighbors, then you put it in the middle of this 4 neighbors. Otherwise, you have many vertices sending many edges there, then you use this operation swap to extend it. Otherwise, again, you find the square path of length 2 over 3, alpha n over 3, and then you connect it using this R. However, in repetition, we use this connection lemma and must say 3 times alpha to the negative 1 type. Why? Every time you do that, the path length increase by at least alpha n over 3. And the length of the square path never exceeds n, so you do it at most this many times, as p prime cannot be longer than n. So what? So we only use 3 alpha inverse times 200, which is like smaller than alpha to the negative, say, 5, which is negligibly small. So we can keep using this connection lemma until when? Until the path P prime covers all but epsilon n vertices in here. Why? Again, I mean, if you have here more than epsilon n vertices, then like the previous one says that if epsilon n of them satisfy this, then you can extend. Otherwise, if it's less than epsilon n, then the number of remaining vertices is more than epsilon n. So there are at least one vertex in T minus U. And then again, by the same logic here, in that case, minimum degree inside of here is large. That means the remaining vertex is at least, I mean, alpha n over 3 vertices remain. There you can find the path and then you can keep repeat. So you stop this if the remaining vertices is less than epsilon n. Then what? Now you have this R, and then you have like this PA, and then P prime, and then very small remaining part T. T has at most epsilon n, and some of the vertices are used, but some remain. And then let's say you have like AB, and then this is CD. Then once again, you go use the connection lemma. To turn this P into a square cycle C that covers all but epsilon n vertices in this. So how many are left? What do you know? So this one has like size at most R, size of R plus epsilon n. And the size of R was like beta to the 20 over. This one is smaller than the alpha to the 20n. And so remember that we have constructed PA at the beginning and we never altered it. So this one is exactly as before. So by observing lemma, there exists. So let's say U is, okay, let's not give, so W is this remaining vertex here. So there exists a path or square path. PAW, which shares both end pairs with PA covering all vertices of the PA as well as W, or the remaining one. And this gives a square of Hamilton cycle. So this proves the approximate version of Posa's conjecture. Okay, yeah, so this is one example of observing method. There are much more, variants, and this observing method applied to many different problems as well, which like converts an approximate structure into optimal structure. Yeah, next time we will talk about one more way of finding this observer in some different situation where we need some different types of observing lambda. Okay, so yeah, that's what we will do next time. Okay, thank you for listening. Then I will see you in next video.